Okay, we're doing a system check on a Amana/Goodman system. 9707, built in 1997, 7th month. It's A42-10. -10 means it came with a 10 kW heater. Back in the day, they came with the heaters already in them. So the first thing we're going to do is shut down the power and make sure it's shut off. Both those are off. We'll test the voltage inside to make sure they're off, and then we will move on to checking all the components in the system that are that you need to check when the power's off. Things like the capacitors for the blower and the capacitor outside and things like that, and the contactor. So we'll start with that. Alright, we have our Goodman coated coil. This is, I believe it's like an epoxy painted coil that Goodman came up with to prevent leaking and things like that. It's a very nice coil. 12.5 microfarad capacitor, blower motor, got our transformer, our infamous Goodman blower relay, our sequencer, and our main power in. So we'll double check to make sure we don't have any power there. Our meter set up here. And got my leads on both sides there, and as you see, we do not have any power, so we're good to go. The first thing we'll do is we'll check that capacitor. During the spring maintenance, I changed this capacitor, so it should be good to go, but we'll double check it anyway. Looking for microfarads there. And we are well within our rating of plus or minus 6%. In fact, we're a little bit over 12.5, so that is good to go. Okay. What we're going to do now is I'm going to cover the door, turn on the blower. We'll check the amperage to the blower. Let's see what speed we are on. Looks like we're on high speed right now. So, all right, both of our breakers are off. We're going to turn the one here back on for the air handler. Now we're going to hook up our amp clamp. What a nice headlamp. To our high speed blower wire. Okay. High speed. We got the amp clamp hooked up to the high speed blower wire. We're going to turn on the blower. I'll block the door so we get a more accurate reading. Alright. The blower is on and we're running about 2.2 amps. Alright, I need to know the voltage on the blower section. So I'm going to put my leads here and check the exact voltage. We are 247.5. Alright, we got our amp clamp in place on the main lead. What I'm just checking for is that the heat strips are pulling the proper amount of voltage. We know the blower will pull just over 2 amps. It'll probably pull a little bit less because we're going to leave the door open. We're just going to turn the strips on themselves and see how many amps we get. As you see, it's a 10 kW heat strip. There's 2 rows of nominal 5 kW. So we should be getting a bump of about 40 amps. So we'll see. Alright, we got 47 amps on the heat strips, which ends up with about a bump of, I don't know, 44, 45 amps. Everything physically looks good in the cabinet of the air handler, so the air handler's passed the test. Okay, now we're going to measure airflow on the return grills. And what I like to do when I do this, I don't always have the exact model of return grill, but I do go to Hart and Cooley, the engineering stuff, excuse me, and I pick out a grill that's close. Now, they didn't have the size that this particular grill was. So this particular grill is 16 by 20, or 20 by 16, but there's a 12 by 12 around the corner. And if I look at the 12 by 12, I can see that the AK factor is 0.66. That's the free area on that grill. So what I do So I know 0.66 square feet is the free area on a 1 square foot grill. Then I know that I can multiply 0.66 by these measurements and get the free area of those grills. So I'll go to 16 by 20 times 0.66. I'll get 211.2. So the grill here, and there's one around the corner that's the same size, will be 211. The one around this way will be 144, which is 1 square foot in inches, times 0.66 equals 95. Okay, so I use those two numbers to figure out what I'm doing here. Alright, so I'll get the DAFM3, which is my UEI anemometer. Turn it on. See, it starts up like this. Alright, we'll go to mode and hold the key down. And we're looking for area. And we'll go to 211. And we'll hit enter, and the recording will count down from 20 to start. Or I can just hit record and it'll start. So I'll hold it up, let it get kind of up to speed here. Then I'm going to hit record. You get about 30 seconds, so you can, I usually do about 4 swipes across the grill. And try to make it so I'm about halfway done at 15, so I get a pretty even representation of the airflow across the grill. Try to stay pretty even as much as humanly possible, but it is a human measurement. So what it says here is I have 413 CFM across this grill. Alright, so I'm going to go around the corner. And I'm going to go back and start it again. I'm going to give it a second to get up to speed. Hit enter. And slide it down through there. $355, so about the same. So we're looking at just shy of 800. Now let's go around to the 12 by 12. And we're going to go back, and we were at 95. Hit enter. Let it get up to speed. Start measuring. We got 304 actually through that much smaller grill. A little bit faster face velocity for whatever reason. Maybe the filter is less dirty, or I'm not sure. 304. So we got about 1100 CFM, which is pretty good because we got a 3-ton unit outside. The grills are whistling in here. That's more probably to do with ductwork and grill sizing than anything else. So we've confirmed the CFM is correct, and it's looks like to be about let's see, 304. 304, 400. It goes 355. We're looking at around 1059. So just shy of 1100. Okay. Alright, here's our outdoor unit. Looks like she could need a little coil cleaning, to be kind. Looks like hell. Looks like a tree almost fell on it. Alright, pull our disconnect out. Get our trusty tool bag. There's a third screw up here, but after about the first year, the Goodman units all tend to lose that. Some of our components here: defrost control board, starting PTC, dual run capacitor, contactor. And that's about all she wrote there. Got our power off here, our power off inside. So what I'm going to do is disconnect two yellow wires to the contactor and ohm out the contactor. Alright. Set the meter to ohms. Electrical resistance. Shadowy. Terminals on one side. The other side. 18. Good to go. As long as they're above 10, I'm pretty satisfied. This one is good, not above 20. So, good times. Things working good. So now we're going to go for the outdoor capacitor. 3 terminals. You have your brown there. It's going to be going to your fan. You have 2 wires here, one from the PTC, one from the compressor. Unplug those. These are pretty easy because they're all color coded. 3 reds are all your run circuits there. Just put them all over in the same spot so you don't forget about them. Despite what you see me doing, you can discharge the capacitor before you work on it. You don't see me doing it, that doesn't mean you shouldn't be doing it. I know that I'm not going to get zapped after a certain amount of time. Usually it discharges into motor windings and things like that. But for the purpose of everybody else, discharge your capacitor. Don't get mad at me when you shock yourself. Alright. Set it up for microfarage. We're going to go for common. That's all those red wires. To Herm. Letting it build up there, and we got a 40/5, and we are still in the good in that area. Alright, let's see about our /5. And we are still in the good in that area. So 38.5 and 5.2. Good. Always make sure they're nice and tight going back. So put the power back to it and record the line voltage. $247.4. Good. Alright, we're going to check our wet bulb again. It's been a few minutes. We'll check it on the check it on the supply and return again. Right now, I don't know if you can see it or not. It says 52.2. See if we stay around there. 52.75, yada yada yada. Coming down. 51.4. Seems to be holding there. 51.4.3. Okay. More balanced. Got 57.2.4 coming back up. 58.5. So got 51 or so, actually 51.3. And now we got a return side of 59.5. We got our entering temperature on the condenser. Running at a superheat of 24, and subcooling of 4.3. We're going to call her 75. There we are. Alright. We got our indoor wet bulb, outdoor dry bulb. We're going to enter. We were 59. Oh gosh, I think it was 0.5. We'll see. I know that's pretty close. 75 outside. Target superheat of 11. We're a little high here, so we may need a little bit of charge. Yeah, we're a little bit high on the superheat, a little bit low on the subcooling, so we may need a little bit of charge. We didn't add any charge last time, but the first time they came out, when I put in that coated coil, we did add a little bit of charge. So maybe there's something kind of slow leak happening here. Could be. We'll let it run for a few more minutes and see. We'll go ahead and get our amperages for the compressor and outdoor fan motor. We have our compressor wire coming off the contactor. 10.8. See, our rating is 16, so we're well within that. 10.8, and now for the fan motor, we have 1.4, and our rating for that is 1.8, so we're good to go there. Make sure we record all these because we track them from year to year, see how they change. There's going to be some change because of conditions, but you can get a general idea if things are going bad before they go bad. See, our superheat's come back down again. Looks like our charge is pretty close, so we'll stop this charge test here in a second. We'll put in the heat and make sure it's performing in heat. There's no issues with the reversing valve or anything like that. Alright, the unit's in heat. It's going to stabilize over the next several minutes. Let it run for at least 10 minutes in heating to get a good idea about the pressure. There is subcooling coming back from the condenser coil inside. What was the evaporator coil and cooling is now the condenser coil. Hot gas is sent into that coil and condenses across the 1100 CFM of air that's flowing through it right now. It's condensing at a rate that's producing 7 degrees of subcooling. That'll increase as the pressure increases. We still have the clamp on the same spot because it's the exact same reading, just in heating mode. It had 15.6 startup amps, which is pretty good, and that's due to our PTC up there. It's pretty cool out today and probably hasn't been starting to stop in a whole lot, so the PTC hasn't had time to be awful. But right now it's doing its job. So we'll give it a few minutes and we'll check on it again and check on a temperature rise inside. Okay, as you see, the temperatures have come up in the heating mode. There's 30 degrees of subcooling now. And they're continuing to rise, and they'll keep rising for a good while, then they'll level out. And as the temperatures rise in heating mode, you'll have the compressor running at a higher amperage. The amount of energy needed to push that pressure increases as the pressure increases. And the pressure increases basically because it's sending it into a different heat transfer coil. instead of going to the condenser coil outside, during the summer, it's going to a smaller evaporator coil that's now the condenser coil. So you have fans outside that can push several thousand CFM sometimes, and now you got a fan pushing 1100 CFM across it. So there's a pressure difference. As you see, our compressor amperage will continue to rise. 16 amps was the rated load amps, so we'll see how close we get to that. I don't think we're going to be too awful close to it. We should be bottoming out here pretty soon with our pressures. Everything looks pretty good. I don't suspect any problems as far as the reversing valve. If it was still in cooling, obviously we'd have a reversing valve problem. Or if the pressures were a little bit whacked out, like you had a compressor valve problem, I would suspect the reversing valve. I always check the reversing valve in heat pumps. Not too long ago, I had an apartment building where they told me the compressor was bad. It was the first time I'd been there. I told them I'd take a look, and it was actually the reversing valve. And the hot gas going through the reversing valve back to the compressor was so loud it was making a whistling sound. So it was pretty apparent to me when I walked up. But it just goes to show you that, you know, it's some diligence with the reversing valve, because it can present symptoms that appear like compressor issues. But we look pretty good here. 11.8, so we've actually come down a little bit. So everything's looking pretty good as far as the heating mode. Now I've got the mega ohm meter hooked up, just so we can check the heat pump in particular. We'll see how it's looking. Looks like everything is good as far as mega ohms, so I know that was one of the worries of the owner, that his reciprocating compressor was going to crap out one day, but it looks like it's going to be fine for the foreseeable future. This coil has a date with Destiny. That Destiny is the coil guy. Now this coil wasn't extremely dirty. I don't think it's ever been super clean, so we're going to clean it since we're here and this is our job anyway. Make it nice and clean and shiny and beautiful, and remove any little bit of dirt that's in there so it doesn't start building up. Okay, the next part that we need to do is calculating the BTU for the system. We're going to take our wet bulb supply and return temperatures and convert them to enthalpy numbers. So basically what that is, think of it as the amount of energy in the air, because your air conditioning has to cool the air sensibly and take the humidity out of the air, latent cooling. So you have both of those. So we're going to go first to see that our indoor wet bulb was 59.5 and a supply wet bulb was 51.3. So we'll go to the enthalpy chart. We find that 59.5 we're at 26.12, and at 51.3 we're at 21.03. So what we're going to do is make an equation where we take the difference of those two numbers, multiply them by the multiplier, which is 4.5, then multiply them by the CFM, which was 1060, and we get 24,279 BTUs. So even though we have a 3-ton heat pump, it's only putting out just over 2 tons of air conditioning. The next step is we are going to take that BTU number and we're going to calculate ER. So the next thing we need to do is calculate watts. Alright, the next part we're going to do is figure out the wattage of the unit. At the condenser, we have 247.4 volts. We multiply that by 12.2 amps, and we get 3,018 watts. Another way to say watts would be volt amps, which is obviously volts multiplied by amps. At the air handler, we have 247.5 volts multiplied by 2.2 amps. We get 545 watts. The total system watts is 35.63. Now that we know that the system is about 3.5 kW, we can take it to the next step which is dividing the BTU 24,279 by the wattage 3563, and we get a very energy efficient, sarcastic 6.8 EER. So the diminished BTU, the restricted airflow, are the reasons why this system functions at this level, which I'm sure it probably always has, because the duct system is very old. We have 3 filter grills and they have highly restrictive filters in them, so it definitely doesn't help. I guarantee that if we change filters, we could probably get 100 or 200 more CFM out of that system. It's poorly designed now. The 3 of the grills have a tremendous amount of airflow, and the ones in the back do not. So the customer has expressed that he would like to change out the entire system at one point, so we're probably going to wait for that. But this report may hasten that. So we'll see. That's about it. And I'll fill in my form, and I always mail a form to the customer with all this information on it. And so he'll have all the information he needs, and he's aware of everything that we do. So there's no doubt, what's the guy doing there for an hour and a half, just wandering around, and I'm actually doing stuff, and I'm measuring things, and I'm keeping track of these amperages year from year, making sure all these motors are running at the proper amperage, there's a proper voltage coming in, the capacitors are good, the subcooling and superheat's good, and that's about all for my preventive maintenance till the next one.